Hello, this tutorial is on nuclear magnetic resonance, also known as NMR, and in this series of tutorials we are going to have a look at spectra like these, which can identify compounds for you. So you should be able to understand by the end of this topic how to read these spectra and be able to identify the compound that they are referring to. In this particular tutorial I'm going to go through some of the features of these graphs or these spectra, explain kind of where NMR comes from, how it comes about, and then we're going to start looking at carbon-13 NMR as one example. Okay, so NMR stands for nuclear magnetic resonance, and it's a way of determining structure of a compound using the nucleus of the atoms within that compound and placing them within a magnetic field so that the nuclei can align with a magnetic field. So for the sake of NMR, you need to imagine nuclei, particular carbon-13 nuclei and hydrogen-1 nuclei, kind of like little magnets where they can align themselves with an external magnetic field. So if you've got a big magnetic field and you place a little nucleus or an atom in it, the nucleus will align itself with a magnetic field, kind of like when you put a compass next to a magnet, it will align itself with that magnetic field. Now, not all nuclei will do this, only certain ones, and the ones that we look at A level are hydrogen and carbon-13. You don't need to know why they do this, and you don't even really need to know that they do this, but it's a nice background to help you to understand where this comes from. So once you've got the external magnetic field and you've got your nucleus and it is aligned with your magnetic field, if you were to hit it with some radiation, something to provide it with a little bit of energy, you can get that nucleus to flip upside down so that it's aligned against the magnetic field. Okay, so now I've got a nucleus flipped upside down. Now, this nucleus will naturally relax back to the way it was before. So after the pulse of energy that's flipped it upside down has passed, this nucleus will turn itself back around and will face the way it was before and align itself back with the magnetic field. And as it does so, it will release the energy again, so that it falls back down into its lower energy state. So you can kind of picture it as having two energy states. One where it's aligned with the magnetic field, that's low in energy, and one where it's aligned against the magnetic field. So to get it to jump up in energy, you have to supply some energy, and then as it naturally flips back the other way, it will release some energy again. So that's what nuclei are doing when they're in a magnetic field. If they are hit with some energy, they can align themselves against the magnetic field and then they relax back again. So this is exactly what NMR is based on. It is about representing the interaction between the energy that the nuclei are hit with, the magnetic fields that they are aligned with or against, and it represents each of these interactions as a peak on a graph that you can then interpret. So I'll show you what this looks like in terms of the machinery that's used. Okay, so this is what the machinery would look like for NMR. This is how it works. So your sample is placed into the NMR machine. We've got magnets here, so we're placing the sample within a magnetic field. Radio waves are fired at the sample so that the nuclei flip so that they're now facing the opposite direction so that they're aligned against the magnetic field. Then we have the radio wave output so that as they flip back, they release energy. This energy that's released is detected. It's amplified so that we can actually see it ourselves, and this signal is presented as a graph, which we saw on the first slide, so it's called an NMR spectrum. So one common use of NMR that you will have probably heard about before is MRI scanners. So these work in exactly the same way. It's the nuclei inside your body that are aligned with a magnetic field. They are hit with a radio frequency that will flip them so that they're aligned against the magnetic field, and as they relax back down to their lower energy state, that energy is detected and amplified, and that helps us to visualise what's going on inside the body. So it's exactly the same process. We just don't call it NMR in hospitals because nuclear magnetic resonance would probably frighten people. So we call it magnetic resonance imaging instead, which is MRI. But that is the basis of how it works. Okay, so to be able to get this to happen, to be able to get the nuclei to flip into the opposite orientation, you need to have the correct magnetic field and you need to supply the correct amount of energy, so it's the precise amount of energy that will get it to flip to oppose the magnetic field. Now, for a carbon atom or a hydrogen atom, you might assume that it is a standard radio frequency and a standard magnetic field that would get a carbon atom to flip, standard field and frequency that would get a hydrogen atom to flip. However, if you consider that within a compound you've actually got lots of other things that might affect the magnetic field experienced by a nucleus, they actually take different frequencies and different magnetic fields to be able to get there. So some NMR machines work on changing the radio frequency and keeping the magnetic field the same, and some work the other way around. So I'll show you some compounds. So on these, we've got hydrogens highlighted in red. And what we say is actually not all hydrogens are equivalent to each other in terms of what they experience in a magnetic field. So if you have got a hydrogen that's got bonding electrons around it, so obviously all of these have got bonding electrons, those electrons will reduce the magnetic field experienced by that hydrogen nucleus. So whatever magnetic field you assumed that you would need for a hydrogen atom, when it's got bonding electrons around it, which are reducing the effect of that field, actually the magnetic field needs to be increased a little bit to be able to get that hydrogen nucleus to flip. Equally, it depends on what else is nearby. So if you have got electronegative atoms, then the opposite happens. So if we have a look on the left here, we've got carbon and the hydrogen has some bonding electrons. These electrons are going to reduce the magnetic field experienced by this hydrogen nucleus. On the other side, we've got an electronegative atom here. So these electrons that would have been in the centre have been pulled towards this electronegative atom, so they are further away from the hydrogen nucleus. So their effect of reducing magnetic field here is much lower because the electrons are actually further away. So the magnetic field needed in this example is going to be lower than the magnetic field needed for this hydrogen nucleus. So that leads to this issue of different hydrogen environments. So to be able to understand how many peaks you are going to get in your carbon spectrum or your hydrogen spectrum, you are going to have to understand how many different hydrogen environments you have got. So we would suggest that this hydrogen is in a different environment to this hydrogen. It takes different conditions to be able to get that nucleus to flip, and therefore it will release a different amount of energy when it relaxes back into its normal state. And we get exactly the same thing in carbon NMR. So if we bring in a carbon example, we've got here some carbons that are in different environments. So for example, we have got a carbon here, which is right next to an oxygen. So this is a very electronegative atom. It will pull these bonding electrons towards itself, leaving the carbon a bit more exposed. So it will experience a higher magnetic field than, for example, this carbon 6, which has just got hydrogens and other carbons around it. So one of the first things you need to be able to do is to be able to count how many different hydrogen environments you've got, how many different carbon environments you've got within a compound, because that will tell you how many peaks you are going to get on your NMR spectrum. And once you know how many peaks you've got, you need to understand whereabout they are going to appear. So if you had, very simply, a spectrum that looked like that, just number of peaks, we've got 4 peaks, so you've got 4 environments for whichever nucleus you're looking at, but the distance between them is important. Whereabout they appear on this axis is really, really important. So I'll just show you a proper spectrum for now. So here we've got the spectrum that would be produced by the carbon-13 NMR of this aromatic ketone that we've got here. So to be able to identify how many peaks you should have, you need to be able to identify how many carbon environments you've got. Now in this compound you have got 1, 2, 3, 4, 5, 6, 7, 8 carbon atoms, but that doesn't necessarily mean that you have got 8 carbon environments, because some of them might be equivalent. So if the carbons are in symmetrical positions, they are exactly equivalent to each other, so their peak would come out at the same place, so it would only appear as one peak. So this carbon is obviously on its own. This is one environment because there's nothing else around here that's similar to this. It's a methyl carbon. Same with this carbon. This is a second peak because this is the only carbon that is double bonded to an oxygen. And then around here, we've got all of these carbons and hydrogens. Now each of them is bonded to a carbon and a hydrogen, and has a delocalized electron that takes part in this, this benzene ring here. So if you look at the symmetry, there's a plane of symmetry through here. So we can assume that that carbon is in its own environment because it's got the carbonyl group right next to it. But these two are in exactly the same environment because there is a line of symmetry. So that carbon with one hydrogen coming off it, if you follow it around that way and you follow it around that way, it goes to exactly the same atoms as this carbon attached to one hydrogen there, if you follow it that way or if you follow it that way. So this carbon and this carbon are seen as being in equivalent environments, so they will only produce the one peak. And the same happens here with this carbon and this carbon. If you go to the left on this one, you go from a carbon with a hydrogen to a carbon with a hydrogen. And here you go from a carbon with a hydrogen to a carbon with a hydrogen. And if you go the opposite way, CH, the carbon that joins the aromatic group to the carbonyl, then the carbonyl, then the methyl. Same happens here. The CH, the carbon that joins the carbonyl group itself, and the methyl. So these two are also in equivalent positions, but they are not equivalent to these two. So we don't have all four in the same environment. These two are in the same environment because they've got the same connectivity no matter which way you go. And these two are in the same environment. So we've got so far 1 peak, 2, 3, 4, 5, and then we've just got this carbon left on its own here. So this is going to be our 6th carbon environment. Now we do some practice of this in lessons to help you to understand how you identify environments. So 6 different environments, even though we've actually got more carbons than that, will give you 6 peaks on your graph. So you can see we've got 1 peak, 2, 3 right next to each other, 4, 5, and the 6th one over here. So chemical shift is the value along here, and it's measured in parts per million. And your peaks are shifted to the left if you're near to some electronegative groups, and to the right if you're not. So you can, little kind of trick, you can assume that this end of the chemical shift axis is kind of the interesting end, and then this end is like the boring end, because this is where you're going to get your C's and H's. This is where you're going to get your electronegative atoms like oxygen and so on. Now, usefully, in your exam, you are given the chemical shift for various functional groups. So you'll be able to look at a peak and then compare that to your data table in your exam, and it will tell you which functional groups correspond to that peak. So a lot of it is just using your data table and being able to understand which peaks represent which functional groups. But you can see that within this, you've got a fairly interesting group here with lots of equivalent carbons. You've got a very interesting group here because you've got a lot of electronegativity difference here with the oxygen pulling electrons this way. And then you've got a very boring group here. So based on my little trick of the interesting end and the boring end, I could suggest that this peak here is going to be the alkyl group, so this is going to be your methyl carbon. The very far end, this one, is going to be your carbonyl group, and the ones in the centre, although I couldn't suggest which ones are which without any further knowledge, I could suggest that this represents the benzene ring. And that's what you need to be able to do. So you need to be able to understand what each of the peaks represents and be able to consider what structures you might get from that. Okay, so chemical shift is really, really important, and it is here on this axis, measured in parts per million, which basically means if you go up by 20, all it's suggesting is that you would need a magnetic field 20 millionths stronger to be able to get that nucleus to flip. So don't worry too much about it. You do need to know that it is denoted delta, so chemical shift is called delta, and it's measured in parts per million. And then beyond that, it's simply a case of looking up your data tables and figuring out which functional groups they're likely to represent. Now, the last little bit on chemical shift is that this scale actually needs to be measured relative to something. So when you put your sample, this, into your NMR machine, you also have to put in a standard, which this is measured against, like a reference sample. And the reference that we use in NMR is called tetramethylsilane, or TMS. And It's a silicon atom with 4 methyl groups. Methyl groups coming off it. And this works for both carbon NMR and for hydrogen NMR because it's got plenty of carbons and plenty of hydrogens. It's got 4 carbon atoms that are in equivalent positions. So on a carbon spectrum, that would give you one nice solid line because it's worth 4 carbon atoms. So if we go back to our spectrum, at 0, there should be an extra peak. It's not very straight at all. Big bold peak there, which is your TMS peak. Now, in lots of spectra, it's removed because it's not actually part of whatever it is that you're looking at. It's just there as a reference to give you that point that says this is 0 and everything else is a number relative to 0. Similarly, in hydrogen NMR, TMS has 12 equivalent hydrogen atoms, so that will give you a really solid base peak on a hydrogen NMR as well. It's also unreactive. So you might be asked about what the benefits are of using tetramethylsilane as your standard in NMR. It's unreactive because obviously you don't want it to react with this because then you'll get a different set of peaks for whatever the product is. It needs to just sit there and be detected. So it's unreactive. It's volatile, which means you can remove it very easily by heating. So you can take it away and get your sample back. And it's non-toxic as well, so it's easy to handle and easy to use. Okay, so that's the background, that's the basics of NMR. The 2 different types we're going to use are carbon-13 and hydrogen-1. Hydrogen is quite a lot more complicated to interpret, so we're going to start with carbon-13 because it's fairly simple. So carbon-13 is purely looking at how many carbon environments you have got, that's how many peaks you're going to have, and looking at the chemical shift to figure out where about those peaks are going to appear on your NMR spectrum. Then once you've practiced doing this, what you'll be able to do is look at a spectrum and be able to draw the structure from it. So we're going to start with carbon because it's nice and easy. So you'll be given a spectrum, fairly simple, looks something like this. Your peaks will be nice and clear and there won't be too many of them with carbon-13 NMR. And you'll have a chemical shift that goes from 0 up to above 200, so maybe 220 parts per million. So this is delta, measured in parts per million. And then it will be a case of understanding that you have got 3 different carbon environments and looking at the delta value, comparing that with your data table, figuring out what functional groups you've got. And then you can put that information together to be able to determine what the structure will be. So quite often you'll be given the molecular formula for something, just like C2H6O or something like that. And you will need to look at the NMR spectrum and figure out what functional groups are in it and therefore actually come up with the structure rather than just the molecular formula. And that is it for your intro to NMR, which I'm sure seems a little bit baffling at the moment, but I will add more tutorials that will go into different types of NMR in a little bit more detail, and we'll show you how you can actually elucidate the structures from the spectra. So I'll do some examples of that in future tutorials.